Okay, so I think we are now live once again. Welcome back, everybody, to another edition of Quarantine Thermo. It's a great pleasure to have with us a pioneer in the field of experimental information thermodynamics this week, Professor Felix Ritort from the University of Barcelona. And so just before I hand over to him, I'll just explain the format, as always, to those of you who may be new to this series. So Felix is going to speak for us uninterrupted for 45 minutes to an hour, however long he wishes. And then at the end of the talk, we're going to have question and answer session. So you can ask questions to Felix about anything you're curious about by just writing them in the YouTube chat window, either at the end of the talk, or if you have questions along the way, feel free to just write them in the chat window, and I'll pick them up and I'll pass them over to Felix and he can answer them at the end. So with that kind of all clear, let's move on to the science. So Felix, I think you're already set up, so please go ahead.
Okay, so good afternoon to everybody. It's a pleasure for me to do this experience of a webinar. So actually, this is the first time I give some kind of talk online at a distance in this way. What I'm going to try to talk about here is to explain you some of the latest experiments or some sort of the review of some of the experiments over the past few years we have been doing in my lab to measure thermodynamic information. So, as you well know, single molecule experiments have been very successful in evaluating, in measuring free energy differences, especially in small systems, like, for example, molecules with a few number of states. And what it turns out to be interesting too is that these same experiments that provide access to free energy differences provide also access to information. And following this statement by Lord Kelvin in the 19th century, you understand something. You start understanding something when you can measure it and when you can give a number to that quantity. So that's our leitmotif to start to do this kind of research. So let me just start a brief review or reminder about force spectroscopy, which is a technique that we use in my lab. And in particular, we use optical tweezers that, as you know, are instrument devices capable of exerting very tiny forces by measuring the change in light momentum carried by a laser beam. Now, this invention of laser tweezers was recognized 2 years ago with the Nobel Prize in physics, which was given to Arthur Ashkin in one half for this discovery of or invention of optical tweezers, but also the other half shared between Muru and Strickland for the invention of high intensity short time pulses in laser physics. So this invention of laser or this invention of optical tweezers has been extremely useful in biophysics because it allows us to measure very small forces operating at the molecular level, and at the same time it allows us to use light to manipulate these molecular objects. Now, I was very proud. I had this invitation in December 2018, barely 1 year ago, to go to Stockholm and to enjoy the ceremony of the Nobel Prize. Now, related to this, I want to just tell you that the main contribution or the main concept behind optical tweezers is this optical gradient force, which is the fact that if you take a laser beam, which is monochromatic light, collimated, so incoming rays are parallel and perpendicular to this lens. If you take a lens of sufficiently high numerical aperture, then you can make the rays converge to a focal point with a big angle. This big angle means that the deflection of the beam of these rays, high angle rays, by an object like this sphere that you see here, this sphere has an index of refraction higher than the surrounding. The surrounding can be vacuum, air, can be water, whatever you want. But if you have an index of refraction higher, the fact that you have high angle deflect rays, incoming rays on the surface of this bit, means that you can have a strong angle deflection as given by the Snell's law, and therefore you have a strong change in linear momentum, which is capable of exerting a restoring force, which is this force here that you see as a contribution of these two rays, which is higher of the component, which is called the scattering component, which is usually much higher when you have low angle incoming rays. So this high angle rays by a high numerical aperture objective is the principle that makes the optical tweezers operate by taking advantage of this optical gradient force. Now we can implement this principle of the optical gradient force in instruments, and you may have seen many different kinds of instruments that operate or are based on the same principle. Here in my lab in Barcelona, we use an instrument, a device that consists of two counter-propagating beams in such a way that the counter-propagating principle permits us to relax the high numerical aperture condition of the objectives, and then by using the fact that the scattering force counteracts and cancels out between the two objectives, the two lenses, then what we can do is to increase the gradient force to basically double the gradient force, the optical gradient force, and the scattering force being minimal. And the idea of using low numerical aperture objectives means that we also don't lose much light that can be collected in position-sensitive detectors, the so-called PSD, at opposite ends of the beams. Okay, and then by collecting the amount, and of course by collecting with these position-sensitive detectors, by collecting the point at which the beam collides with the detector, we can measure directly the change in light momentum. Therefore, we can measure directly the force. And now you see, this is the instrument that we have in my lab, which is very compact. It's called mini tweezers. And here is an illustration of how we use it to pull a molecule. So here you see we produce this counter-propagating optical trap by two beams, in which we capture one small bit, and this is our force sensor. We have another bit in the tip of a pipette, and in the middle we have a molecule that we can pull by moving the beams relative to the pipette, and therefore we can stretch any molecular construct you may put here. So here I show you an example of an antigen-antibody interaction, which is very important, for example, in immunological recognition. But you could put everything. You could put a DNA, an RNA, you could put even this famous RNA coronavirus of I don't know how many thousands of base pairs. You could put it here, and you could study how it responds to mechanical force, to mechanical stress. Okay, and that's important because in doing these experiments by exerting force, we can somehow challenge, or we can probe different conformational states of the molecule. Now, what I show you here in this slide is what is the simplest experiment in the single molecule field, which is the pulling of a single DNA molecule. Now, this experiment, since 30 years, approximately 30 years, has become a standard in many labs, but it's a remarkable experiment because it shows you that the dream of manipulating molecules and controlling molecules can be achieved with this sort of experimental techniques, with this instrument. Okay, and the experiment is summarized in this green box, in which you say, okay, take a single DNA molecule, exemplify it here as a cord, and pull from its extremities. Instead of using a guy pulling from the cord, you use an optical trap with a bead. Okay, that this bead in the optical trap is like a spring. So this spring pulls from the DNA. Okay, and you do in this way, you record the force extension curve. So this experiment can be done. The only thing that you need is to prepare your molecules, label them at the ends to bind specifically to conjugated beads. Okay, these beads have been treated chemically to bind specifically to these small molecules at the end of the DNA. And then one bit is in the optical trap, the other bit is in the pipette. Okay, let me show you an animation, a movie of this experiment. And here you will see, this is the pipette, and here you have the optical trap. Here is water, everywhere is water. We move the optical trap, excuse me, we move the fluidics chamber, okay, with some motor stage, and then we use the optical trap to capture a small bit. We reposition the small bit on the tip of the pipette, and by putting a syringe that is coupled to the end, to the bottom end of this pipette, we can basically immobilize the bit, as you see here, on the tip of the pipette. So here, just if you look at me in your screen, in your image, in the video camera, you just take a syringe and you pull away air out of the pipette, and then you, by air suction, you need a very tiny force, actually. This is 10 microns, so this bit is typically about 2 microns. It's a very small object. It's a very small amount of air that you pull out that you can immobilize. This is called micropipette aspiration, which is, by the way, a technique widely used in biophysics to experiment, to manipulate even single cells. Okay, let's not go into these details. Let's continue watching the movie. Now what I will do is I will move the fluidic chamber and then position this light point here in the middle of my screen at the end of a supplier tube with beads of another size that have been incubated with DNA. And the beads are conjugated with a molecule which is called anti-deoxygenin that binds, anti-deoxygenin is an antibody that binds specifically to the end of the DNA molecule. And now it starts experiment. I stop the movie now. You start moving the pipette relative with this bead immobilized relative to this bead. Here there should be like small molecules protruding from the surface. And I start moving the bead in the pipette relative to the bead in the trap. And this molecule that we have here incubated with the beads is about 8 microns long. Now, in the molecular world, 8 microns should be something in contour length like this distance, because it is 10, so I should expect something like that. Now, the point is that in random, when subject to thermal forces, so in the Brownian world, determined by the collisions of the molecules of water, the molecules are not extended. When you go to very short scales, in the presence of thermal motion, and when the typical energies, like the bending fluctuations of the polymer, are on the order of kBt, the typical structure of a polymer is a random coil. So it's forming like a collapsed polymer, which even if it is 8 microns long, you cannot expect to reach at this distance. You are never going to fish the end of the DNA molecule. At this distance, you should approach the surface of the bead. And this is what you see here in the movie. It is only when I approach really the bead in the pipette to catch the end of the random coil that I get the connection. And here you see an animation. Well, that's a real movie. It's not an animation of this polling experiment. Once I know that I have a single molecule between the two beads, I start moving the optical trap that is here. The optical trap, you don't see it's a filter because the light is too intense. You start moving the optical trap relative to the bead in the pipette, and then you start recording the force as a function of the extension. Okay, so now once you have the experiment set up, you can start doing the experimental measurement to record the elastic response of your DNA molecule. And you can repeatedly do that as many ways you want, many cycles, pulling back and forth until you are satisfied with your measurement. Now, this is what you measure, okay? And this is a typical force extension curve for this molecule of 24,000 base pairs, which is about 8 microns contour length. And you see that the force increases when I reach this dashed line, vertical dashed line, which is the contour length. The forces does not diverge because there is some elastic compliance of the DNA, which is defined by the so-called enthalpic rigidity or Young modulus, okay, which means that I can increase even farther away the length. So here the molecule is overcoming its own contour length, but at some point there is this plateau, which is the so-called overstretching transition. And this overstretching transition, I won't talk about it, it's a subject of intense research. It's thought to be the consequence of a conformational, is discussed, but it's a sort of many conformational transitions between different phases, among them the initial bDNA phase, also the overstretch, the so-called sDNA phase, Here is the sDNA, stretched DNA at this end, and in the middle there are many transient conformations like partially melted DNA or partially frayed DNA. Frayed means that the ends of the DNA pull out from the surface of the bead. And here there is this regime, very interesting, which is the entropic regime of response of the DNA, which is defined by the persistent length. So typically the persistent length is the length along the contour length of the DNA at which you can expect that the orientation of your DNA will completely correlate. Okay, so there is a natural bending and stiffness, and for distances longer than 45 nanometers along the contour length, correlations due to this bending and stiffness are lost. Okay, and the tangent vector, if you want, of your polymer completely correlates. Okay, and here you see a fit, which is shown in this red curve from extension basically, or force basically 0, up to the contour length extension by the so-called extensible warm light chain, which is one of the models proposed in the 50s, 1 century ago, by Fleury, Cracti, Porot, and other people to describe the mechanical response or the behavior, the thermal behavior of polymers. And another experiment remarkable that I want to show you in this introduction is what we can do if we take a DNA molecule and instead of stretching from opposite ends, what we do is we pull out the 2 strands from the same end. And here we don't elastically probe the DNA, we unzip the DNA. So we break the double helix, here represented by a zipper. Every chain in this zipper would correspond to 1 strand of the double helix. So 1 chain of phosphates here, 1 other chain of phosphates. And as you pull apart these 2 ends by contracting forces, so 1 bead pulls from this end, the other bead, for example, in the pipette pulls from the other end, I get this thing here. Okay, until the double helix dissociates. And here what you see, this experiment is different because you don't probe the reversible elastic response of double-stranded DNA, the double helix. Here you probe the base pairing energy between complementary base pairs along double helix. Okay, and you see that you get this sawtooth pattern, very characteristic of the sequence of DNA. Okay, and at the end, I will stop one moment, you get this response, okay, which is the response of single-stranded DNA. So let me tell you that in doing this experiment, I am pulling from the same end a double helix that is ending with a loop, in such a way that if I fully dissociate the 2 strands, I don't get the 2 strands completely separated away from each other, but I keep them at a distance because there is a constraint, a loop, a closing loop at the end. So actually, this experiment, what it does is it converts double-stranded DNA, the double helix, into single-stranded DNA. And that response at the end of this curve here is the elastic response of the single-stranded DNA. So this would be another experiment of elasticity, if you want, described by these sort of polymers that we were seeing before for the double-stranded case. Now, if I continue this experiment, and once I have unzipped the DNA, I rezip my DNA, I observe the following. It's fully reversible. And that's remarkable, okay? Because here you are breaking molecular bonds, and you have a single-stranded polymer completely unzipped, completely dissociated, that reforms to the proper native structure. Okay, this is a common theme in biology, a common topic in biology, because in molecular remodeling, in remodeling of the cells, of all the molecules inside the cell, continuously, every time this is happening, things break and reform again, regaining the original shape and the original structure. And that's possible because the typical energies involved in the breakage of these base pairs are comparable to kBT, which is the source of energy in the form of heat coming from the thermal environment. And because they are comparable, this process can take place reversibly. Okay? So it's actually known that the typical energies that hold many molecular structures together, in particular these 2 strands of the DNA together are on the order of kcal per mole. This is the typical energy in molecular biology, in biochemistry if you want, kilocal per mole, which is about 1 kBt. Okay, room temperature, 1 kcal per mole is about 1.6 kBt. So the typical energies of these complementary bonds is about 2-3 kcal per mole, or even less, 1-2 kcal per mole, so about 2-3 kBt, which is comparable to kBt. If the energies would be much higher, like covalent interactions, which means hundreds or thousands of kBt, you would never see that, and fracture would be irreversible. Okay, well, that's what people say sometimes, the edge of chaos. You know, living at the edge of chaos. You are at the level where the structural stability of these, the energies, the energetic stability of these structures is comparable to a thermal noise. Okay, that it's what makes it actually reversible. Well, this is not important in this slide. You can use these experiments to predict the free energy of the different base pair combinations. What you see here is nearest neighbor base pairs, because it's known that in DNA, the stabilization of the double helix is not just the hydrogen bonding, Watson-Crick hydrogen bonding, but also the stacking between base pairs, consecutive base pairs or consecutive bases along each of the two strands. So this is a doublet of base pairs, AT stacked on AT. Here would be AT stacked on CG and so on. Okay. Now the typical, these are measurements, you said these are measurements by people for many years in biochemistry. Many labs have contributed to these numbers, are called unified oligonucleotide dataset. And this is what we measured in my lab for 2 sequences, and we got results very much comparable, and even with some errors, because these numbers here have not attributable errors, but we see some small corrections. Well, we were able to show that the power of these force energy measurements, okay, using these experiments, it's really very powerful, these single manipulation techniques for the energetics of single molecules. Now you can pull single molecules again and again of many types. I show you here a typical experiment that you do not on a long DNA hairpin, but on a short DNA hairpin, like a few tens of bases or base pairs, or RNA hairpin, also a few tens of base pairs. And you see, you could also do a protein, a few hundreds of amino acids, whatever molecule you want to study. Okay, so here I show you the typical experiment in a DNA. What you see is if you pull, there is the force versus extension shows this increase. This is the response of the optical trap. At some point when the force is high enough, you release the molecular structure that is hidden inside this molecule, okay? And when you come back, you see this hysteresis behavior, okay? Let me show you an animation of this experiment. This is a native structure unfolded. You go back and forth. There is some hysteresis always. The force at unfolding is higher than the force at refolding. There is some lagging time behind the refolding with respect to the unfolding. You could go on and go on, okay? Now, these sort of experiments have been very interesting for non-equilibrium physics because they have allowed us to access new phenomena, like, for example, the so-called jumping over an energy barrier, the so-called kinetics of conformational transitions over conformational changes over transition barriers. So I show you here 2 examples. Well, one example of this, which is these beautiful examples done in the group of Michael Boothside in Canada, where he's able, by looking at very short time resolutions of barely 5-10 microseconds, to see actually how the transition between the 2 levels of force when the molecule opens, so that would be the force rip that we saw before, but in this kind of experiment, you can see that even when you cross the transition barriers, the molecule goes back and forth. So it's not a deterministic motion, of course, it's a stochastic, but you see advection, of course, because you see a net transition from in this case, the folded state to the unfolded state, but you also see these back transitions backwards. So this is typical of diffusive process. So this is what is called a transition, an activated process, which is diffusive. It's a one-dimensional, if you want, in this reaction coordinate, which is a molecular extension, is a one-dimensional Kramer's process with advection and diffusion. Okay, so this is beautiful because you can see that. Of course, you have to go to very short times, and here you see that the time scale, this is 50 microseconds, so the time scale is barely 10, few tens of microseconds. Okay. Another application is to extract free energy differences that most of you know because you are in a webinar about stochastic or let's say quantum thermodynamics, but you have heard about these non-equilibrium equalities, and this is what we did many years ago when we tried for the first time to use this sort of experiments to test this sort of non-equilibrium equalities. So this is the Jarzynski equality that allows you to extract the reversible work, which is delta G, by using irreversible pooling experiments and then measuring the full irreversible mechanical work. Okay? And actually, this is a field in which my lab has contributed over the past years. Here I show you the version that is more from the practical perspective, from the practical applications point of view, the theorem that is mostly used in the experiments. You have a molecule that you can pull back and forth, and you can measure the work going forward along the pulling process when you increase the force as a function of time. And you can measure the work distribution coming back. Coming back means in the time reversal process. So you relax the force at the same speed. Now, if you fulfill this condition of symmetry between the forward and reverse, you know that even if the process is carried out irreversibly, so you have a lot of dissipation, the ratio between the two distributions satisfies this expression. This immediately gives you the Jarzynski equality, okay, because you can switch this exponential to the left-hand side, you can integrate over all the work values, and you get this Jarzynski equality expression. Now you see here to experiment in a molecule that is pulled, it's very important that you realize that this is the force as a function of the trap position, lambda. Because this is the way how we measure the work. The work in these experiments is measured by looking at the area below the force distance curve. Now, when you pull the molecule, the force as a function of the position of the optical trap follows a red curve, and the area is shown in red. When you relax the forces at finite speed, you find the blue curve. Okay? And typically, this is hysteresis. The typical work value along the refolding is lower than the work value along the unfolding. And this is what you see here when I compare the red curve, let's say, okay, with the blue curves. Here I show you two pulling speeds. So the continuous line is the pulling speed which is lowest, which is 60 nanometers per second, okay, which is about, if you want, 1 piconewton per second of unloading rate or loading rate. And here in dashed line, I show you a higher speed, 3 times faster, 180 nanometers per second. And you see that at lowest speed, the red continuous and blue continuous distributions are closer than for the higher pulling speed of 180, which is shown in dash. And this is because the hysteresis increases as you increase the pulling speed. Now, one consequence of the Crookes fluctuation theorem is that despite of the fact that these distributions are different depending on the pulling speed, so PF is different depending on the pulling speed, and the same holds for PR, the crossing between the two distributions is always delta G. Because for W equal delta G, you get exponential of 0, which is 1, so this is equal to this. So one prediction of this Crookes theorem is that this distribution should cross, at the same value, irrespective of the pulling speed. And this is what you show here, what I show here, with this gray, narrow range, okay, of work values, which gives you an estimate of delta G, okay? So this has been applied in many contexts, has been applied for the recovery of thermodynamic branches, has been applied to non-native states like intermediate and misfolded states in this reference here, and it has been applied to intermolecular binding and to test the validity of possibly among the most important laws in chemistry, which is the law of mass action. But the message is that whenever you can measure work, you can always extract the thermodynamics, okay? But the same holds for information, and that's what I want you to explain now in these 15 minutes I have left, or 20 minutes at most of my talk. You can use the same, not for free energy difference, but also for information. And as you know, information is a fuzzy concept. Because energy, every one of you knows what it is in energy, and is very much agreed by everyone. Entropy is also true. I think that it's very much agreed what entropy is, but information, not only there are a lot of not only information measures a lot of diversity of things, there is also a diversity of ways to understand information, especially from people coming from different fields, okay? Physics and beyond, okay? So, as I said in my, when I start my talk, Lord Kelvin's famous statement, you understand something, or you start understanding something when you can measure it. So can we measure information? And what I want to show you is with single molecule biophysics, we can. And we can get very useful information. Now, I want to start by reminding those of you who may not remember or may not know about the Maxwell Demon paradox. At the end of the 19th century, the great physicist Maxwell proposed a Gedanken experiment, okay? Gedanken experiment means a thought experiment in which one small being, intelligent being, could play with a system originally in equilibrium, okay, to make it go, let's say, off equilibrium, or if you want, it could make a system that was originally in equilibrium to reach another state of lower entropy without further change in the rest of the universe, therefore implying a decrease in the total entropy, okay, of the system, of the universe in itself, and therefore violating the second law. The idea of this demon was that originally a system in which you had molecules, okay, which were distributed according to their velocities with Maxwell, for example, Maxwell-Boltzmann distribution, this intelligent being could use a small gate, okay, could have a small gate, and by manipulating the small gate, he could somehow classify molecules according to their speed. If the speed of the molecule is higher than a threshold value, it's a fast molecule, it's red. If it's lower than the threshold value, it's blue. And therefore, just by measuring the speed of the molecules, looking if they are red or blue, he could open and close the gate to achieve a separation, okay, of the molecules in such a way that red would be in one side and blue in the other one. Now, this system originally was in equilibrium. There was not a temperature gradient. And at the end of the game, you have a temperature gradient, okay, because here it's larger than here. And therefore, this has been accomplished, and that's the paradox, without expenditure of work. Because actually, if this demon is very small and this gate is frictionless, he could do that without expenditure of work. Either because the measuring process could be done in principle without measurement, without expenditure of energy, but also a frictionless wall in a limit can be done also without dissipation. So the whole process could be done without any work expenditure against the second law. There is another version of the Maxwell demon, which is instead of assuming a many particle isolated system, you can think of a one particle isothermal system. So a system that can exchange energy with a heat bath, with environment. And this is the SZILARD engine. So the SZILARD engine is, if you want, a most easy way to implement the concept of the Maxwell Demon paradox. First, because there is just one particle, and this is achievable with current technologies, and also because it's isothermal, and isothermal systems are much easier to perform to set up than systems that are completely isolated. And therefore, this has seen a lot of interest, the SZILARD engine, but the concept is exactly the same. The idea is that you see a particle moving in a container of volume V, okay, which is subdivided, the total volume V is subdivided into parts, V1, V0, okay. In this case, V1 is smaller than V0, it can be other way around, okay. And then you look the motion of your molecule, and then every time you make a single measurement of the position of your molecule, and if it is inside V1, then what you do is you apply a wall, you insert a wall in your system, and you use the collisions of this molecule that now is confined in this V1 volume, the collisions against this wall to produce a movable piston and extract work. And you can do that reversibly, and therefore you could convert, okay, by making these observations, you could lift a weight and therefore extract heat from the environment. So this is in contact with a thermal bath. Energy is conserved, some heat enters into the system and lifts up the weight. Okay, and you could, once you have end up, you start again the game, you see where your molecule is, and now if your molecule is in V0, then you do the same wall inverse insertion, but then you apply the pulling mechanism in the other way, and heat is converted into work. Now, in a series of multiple repeated observations, when when the container is the right one 0, I extract W0. When it's 1, I extract W1, and so on. Now, this is the average work that I would extract if my molecule is found to be in 0, would be minus kBT log P0, okay? Because it's just the change in, it's just the net change in heat with environment, okay? By this expansion. So this is the net heat change is just this expression, okay? Because it's equal to the entropy change of the environment. And the entropy change, you remember, is the logarithm of the volume. So it's clear that you will have the logarithm of the probability here, as the probability is defined this way. The same for W1. So the mean work is the probability of this, let's say, classical Maxwell Demon or SZILARD engine, is the probability to observe, to select a 0, okay, P0 by the average work 0, plus the corresponding term 1. And this gives you this typical famous expression, P0 log P0 plus P1 log P1. Because P0 and P1 are normalized, you get this expression, P0 plus P1 equal to 1. And this equals to the Shannon information of 1 bit, okay? Now implemented this concept in a molecule that can hop between two states, okay? So suppose you take a molecule, and these same experiments I showed you before by Michael Boothside lab, in which you see a molecule hopping between two states. Now the changing force is about 1 piconewton, okay? This is a molecule, it's a DNA hairpin, it has 20 base pairs. 20 base pairs is about 20 nanometers of extension. And with an optical trap of about 60 piconewtons per micron, for example, you get this typical switch in force of 1 piconewton, okay? So now your molecule hops between the two states at constant trap position, shown by this blue level, and every time it does, there is exchange of heat with the bath, and therefore we have the experimental realization of this single molecule SZILARD, okay? We have this experimental realization. We measure work and we measure heat with environment and so on. And therefore, in this experiment, this is a typical dichotomic signal that you observe, okay? And would be the same if you were to make a record of zeros and ones. Here in this SZILARD, you would observe this dichotomic signal. But here I'm measuring explicitly, okay? Now what we did is we characterize this SZILARD. In the SZILARD engine, you can modify or you can parameterize the model by changing V0 relative to V1. So you can decide to make your wall here or there. Yeah? You can partition the volume V, the big volume, in two parts in any way you want. Here we can also partition the two states any way we want, just by moving the optical trap relative to the pipette upwards or lowards. We can just modify the average force changing on the bit. For example, if we, in this experiment, for example, if we work at high forces, or if we move the optical trap away from the pipette, we tend to populate more than folded state, and we get this distribution, okay, in which P1, which is the probability of the folded state, of the unfolded state, is bigger than the probability of the folded state. At lower forces, on the contrary, at lower forces, we have the reverse situation. We populate more the folded state 0 respect to the unfolded state 1. And at the so-called medium forces or coexistent force, okay, which is about 17 piconewtons in this molecule, so we can populate more or less 50% both of them. So we can partition the two volumes in a way, and here I want to show you that the difference in free energy between the two states is just given by the relative probabilities, okay? And this is the detailed balance condition that P0 divided by P1, which is a ratio of these sort of Fermi expressions, is just equal to the exponential of delta G divided by kBT, which is exponential of E. So in principle, we know from this P0 and P1, we could know the free energy difference, which will be an important parameter in our experiment. Now we can implement this single DNA SZILARD, okay, in which we do the same thing, okay, as SZILARD does in his Gedanken experiment. we make an observation. Suppose that we make an observation. We know the two force levels. We are in this condition, for example, okay? And then we measure about 17 piconewtons. Or we measure about 18 piconewtons in this case. We measure about 18. If we measure about 18 at a given time, we know that we are in the folded state because 18 is here too far away from this Gaussian here. So we know that the molecule is folded. And therefore, what we do is we apply a sudden movement of the trap position, delta lambda, in which we stabilize the folded state. So we reduce the force of the overall molecular construct. By stabilizing this state, then what we do is we apply, if you want, it's like inserting a wall in the SZILARD experiment. And now we apply the pulling mechanism. The pulling mechanism is slowly moving the optical trap upwards to recover the original position of the optical trap that we had in the measurement. So we recover the original position, and those transient unfoldings that we observe during this slow recovery is like the motion of the wall in the SZILARD that pulls the weight up, and every time there is this transient unfolding, there is heat from the bath that comes into the molecule, and then we transform it into work. So here you see a work extracting cycle more visually. This is the signal between folded and unfolded, 0 and 1, and then we make the observation at this point. Each folded, we stabilize the state, and then slowly we recover the original trap position, which means we recover these blue trace, okay? And we do that by slowly moving quasi-statically the pulling trap. You see all these jumps down are jumps in which the forces suddenly drops. These sudden drops of the force correspond to releasing the single-stranded DNA of the herpy, and therefore conversion of heat into work, okay? So these are work extracting events. Now you can do this for many experimental conditions and do the work distributions for any experimental condition. 0.5 P0 means coexistence, so P0 and P1 are the same. So the wall in the SZILARD is in the middle, and as I go far away from P0 for 0.5, either by decreasing or increasing P0, it means that I move my wall leftwards or rightwards in the SZILARD imaginary experiment. It's the same thing. And you see the work distributions is a small system. We never measure exactly the same work. So one trajectory will have 5 peaks of work extraction, but another trajectory will have 6, another will have 1, another will have none. I have a work distribution, but the mean, okay, follows this formula, which is called the Landauer limit, which is nothing else than this formula here, okay? Or the Shannon information in 1 bit multiplied by KBT, okay? And this is the, if you want, an experimental demonstration of the Landauer limit. Now, this experiment was done with a classical SZILARD, and what I want to show you is that you can do exactly the same with a new version that we invented in collaboration with Marco Rivezzi, who is now in SPCI Paris, in the so-called continuous Maxwell Demon. This is a new version of SZILARD, which we were surprised that no one since 1920, when SZILARD proposed a model, and until now has been proposed, because it's a solvable model, which is, if you want, the other limit case of what one could imagine to implement experimentally. Now, it's exactly the same as a classical SZILARD. The difference is that you don't just do one measurement. You do repeated measurements, and you decide to extract work only when you see a change in state. So suppose you observe your molecule, and you say, okay, it's in the left compartment. Now you make another observation of your molecule. It's still in the left compartment. Only when your molecule changes compartment, then you decide to extract work, okay? So here is shown as a series of bits. For example, in this case, here is in the left compartment, still in the left compartment, still in the left compartment. Now it changes, now I extract work. Now the nice thing of doing the experiment this way is that the average extracted work is the same expression as before, but you extract work 0 from the compartment 0 when you started observing at 1, because you are waiting for the first change of bit. And therefore, the formula for the average work is as before, but with the weights exchanged. Now, it turns out that you can see that this expression is like before, with a big difference, that now the average work that you can extract is always larger than the Landauer limit, okay, which is the upper Landauer limit, which is KBT log 2. So the average extracted work So the Landauer limit is a lower bound in this sort of configuration, okay, realization of this experiment. Now it turns out that you can calculate, doesn't mean that you are violating the Landauer limit, because the Landauer limit tells you that there is a maximum amount of work that you can extract, which is given, okay, by the information that you stored. And the information that you stored has to be erased, and therefore it needs some heat to be erased. And this energy cost of this information that has been stored, the erasure of this information, is what restores the second law. Now, if you are writing sequences that are not just 1-bit sequences but longer, you will need to erase more bits. Now, it turns out that you can calculate theoretically the information content of these sequences, multiple type of sequences of these bits, okay? And you see what happens. This depends, information content depends on how much frequent are my measurements. And actually, if you make your measurement continuous in time, you make this quantity diverge, because there is a divergence of the information content, which goes like the logarithm of the time between consecutive measurements. Now, you can demonstrate that there is a minimum information which is obtained if you make measurements that are totally uncorrelated. So one measurement, the other, you wait much longer than the relaxation time of your system, whatever relaxation of the system you have, okay? Whatever relaxation time. And you see that this minimum information content has this expression, which has exactly the same form as the average word that you can extract in this continuous version of the Maxwell Demon. There is this added term, but this term, as you can see, is positive, because the log is negative, and therefore this is positive. So it adds up to this term, and it tells you that you satisfy the second law. Now, we experimentally did experiments with this protocol of continuous Maxwell Demon for different P0 values, and we again saw this here is the probability distributions of the word that you can extract, okay? We take positive values for the word that can be extracted, okay? So in average, the work is positive that you can extract. There is long tails in these word distributions. This is the Landauer limit. As I told you, the average work is always larger than the Landauer limit of kBT log 2, but of course is lower than the information content, okay? And here, if you look the average of the distributions, and I show you here the continuous line is this formula here, okay? So it shows you that experimentally it works, okay? Now you can put all the information together, okay? And you can measure, you can show the work for the different realizations of the SZILARD engine. In blue, in red, you can see the classical SZILARD. So the average word that you can extract shown as red triangles with the formula, which is a continuous red line. The work and the Landauer limit is the gray line, kBT log 2. Now the blue is the continuous Maxwell Demon, which has as a lower bound now Landauer limit. It's not an upper bound. You go to the other side of the diagram if you want. And you can also plot the information content you saw in these red lines. R is the relaxation rate of the system. Now, information diverges, tends to diverge logarithmically. If for a finite relaxation time R, you go tau to 0 between consecutive measurements. We are not interested in this limit. We're interested in the fully decorrelated measurements limit, which is the easiest one, and it gives you the minimum information, which of course is above the word that you can extract, okay? While the information, okay, in the classical, let's say SZILARD, coincides, the information content coincides, because it's 1-bit measurement, with the work. So here we don't have coincidence, we have a difference, there is a gap, okay? But of course, this is agreement with the second law. You can also define the efficiency, which is a ratio between the word you can extract with this continuous version and the word needed to erase the stored sequences, so the information of the stored sequences, which is shown on the right axis, vertical right axis, goes between 0 and 1, and it shows the efficiency in orange color. The experimental data in ROMs, orange, and you see that when P0 goes to 0, P0 goes to 1, you go to efficiency equal to 1. So P0 going to 0, P0 going to 1 means that you have a SZILARD where your wall is starts completely crashed on one side, on one of the two sides of the container, okay? So you extract maximum work. Actually, you extract infinite work. Yeah? So it diverges, which is the divergence you see here. of course, the information also diverges. So you are always within the second law. I think I will stop here. I wanted to show you another sort of beautiful experiments that we have done with feedback by implementing this concept now beyond the Maxwell Demon. So not to extract work from the bath, heat from the bath to work, but whether we can lower dissipation in a non-equilibrium system by using feedback. So by pulling molecules, by continuously tracking the state of the molecule and applying some feedback, and use that to reduce dissipation and to improve free energy prediction. That's another use, an advantage of feedback that no one has considered yet. And the answer is yes, but I won't go into this, and I will stop here because I think that my talk has been already a bit long. I want to thank people who have made possible this research in my lab, all the people basically, but these projects I'm discussing now in information to energy conversion are by Marrico, who's shown here, and Marco Rivezzi, who did all the work on the continuous Maxwell Demon. So let me end up with some conclusions here for you to read, and I will end up here with a stop and thank you very much for your attention. Thank you so much.
Thank you very much, Felix. That was really interesting. I can just hear.
You must be very tired. You must be very tired talking for 1 hour. Hearing for 1 hour must be tiring.
No, it wasn't too long actually. I think maybe we'll have some questions even about the feedback material that you weren't able to cover. But yeah, so there's plenty of time for questions. So please feel free to write any questions in the chat window. We've already had a couple of questions that I'll just go through in turn. So and okay, just to relay to you, lots of people are clapping virtually in the chat window, saying that the talk was beautiful, etc. Of course, you can't hear this, but people are very appreciative. So okay, so let's start with a question from Naga Teja or Teja, who was asking. This was at the point where you were showing this force extension curve. So the question was, how do you measure the force actually?
Yeah, so I wish to thank you for this question because actually I didn't know whether to give a very devoted research talk or do some sort of preliminary introduction for theories that don't know about the instrument, which I think is always useful. So your question falls precisely on this sort of quest. So let's say that what we use, the method that we use to measure force is typically what everyone uses. Well, not typically what everyone uses, but is very basically related to what people use in this sort of force spectroscopy instruments. So we have a beam of light, and this beam of light is deflected by the bead, okay? So the bead in the optical trap actually has a full near 100% transmittance. It just barely reflects 5% of light. All light is transmitted. But because the index of refraction of the bead, which is typically silica or plastic, it's 1.3, 1.4, 1.5, is higher than the index of refraction of water. Okay, you need water, that's for sure. If you are in air, that's another story. But it's higher than there is this refraction of the beams going through the bead. So they are fully transmitted. It's like a glass, it's like a lens. Actually, the bead is like these lenses here. But the only thing is that it's not made to focus the beam, it's just to impose a deflection, okay? And we use a sphere, we could use another shape, but the idea is to impose a deflection. If you impose a deflection by this refraction behavior, then there is a change in linear momentum of the light beam. There is a change of light momentum because if you change the direction of the beam, you change, the speed of light doesn't change, but you change the direction of the beam. So there is a change in light momentum. Now it turns out that these detectors here can measure exactly this change in light momentum. By how? By measuring, well, this is from electromagnetic theory, by measuring the Poynting vector. The Poynting vector is a vector that carries energy, but also linear momentum. So P, the energy is P divided by C. But you can measure both the energy and P. And these detectors are done in a way that by measuring the deflection angle of the beam, I can know how much is a change in linear momentum. So summarizing, this is a lens, it deflects the beam. The higher the force, the higher the deflection, because the bead goes away from the optical trap and exerts a bigger deflection on the beam. And from the angle of deflection on the PSD, I can know just by measuring the position at which it collides with the detector, I can know the deflection, and therefore I can know the change in linear momentum. And this is this principle of this lens, of this instrument. Other instruments use another principle, like just calibrating the optical trap, looking at the position of the bead relative to the equilibrium position, and multiplying the displacement with video imaging techniques, measured with video imaging, by the stiffness of the trap. And in AFM is the same. In AFM, you use a cantilever whose deflection multiplied by the stiffness of the cantilever gives you the force. But here in this instrument, our principle is measuring change in light momentum. It's quite subtle and it's quite nice.
Beautiful. Thanks very much. Really interesting. So, okay, so then we had a question from Devira Segal, who was asking about the DNA unzipping experiment. And the question is, what is the role of the solvent? And did you try a different pH?
Well, good question. The solvent is extremely important because this unzipping curve that you see here, okay, in real time, or this the curves that you can see here in experiment, okay, is the same. The experimental curve is shown in black, by the way. So this shape of the curve depends on the typical energies of hybridization of the two strands. Now, what we use in this prediction of these energies, we use the statistical model, and our best parameters model prediction is this red curve, you see, that goes through the black curve. Now, these parameters, which are these numbers actually, depend on all the conditions of your solvent. If you change temperature, they change because free energy is enthalpy minus temperature multiplied by entropy. So even if you assume that enthalpy and entropies are the same, you change the temperature, this shifts. If you change salt condition, this is at 1 molar sodium chloride, you see this here. If you change the concentration of salt, changes. If you change pH, it also changes because pH changes protonation. However, it changes much less. So these experiments have been done by changing pH, but unless you go really to very acidic conditions, then you don't see a big change in the energies. So these experiments are done at near physiological conditions, at least not in salt, but in pH they are done is about pH 7. So if you do pH 6, 7, 8, you get more or less the same. But if you are interested in acidic or very basic conditions, so low pH or high pH, then you would see changes for sure, because protonation will be very important.
Okay, there, thanks. Actually, before I move to the next question, I have a question. I was curious about this. I mean, this plot in particular at the bottom. So is the resolution here, could you actually read the DNA sequence using the force measurements? I mean, is the resolution good enough to actually read a DNA strand this way?
Yeah, so that's a very good question too. It's something we tried to work in the past. Somehow we lost this battle with this because it's not that we tried really, but it's very hard. So you see this curve.
Yeah.
So your question is, Mark, about how can I read GC one strand? Okay. Exactly. The other is complementary. GCTATT from this signal. Now you have to realize that this is a signal in which every 1,000 points here, every 1,000 points here, there are like about 1,000 base pairs. So 1,000 base pairs. So if you take 1,000 here, you would look at 1/10, so which is 100 nanometers. 100 nanometers about 100 base pairs. So you want to put from here to here 1,000 letters, and from here to here 100 letters.
I see.
It's hard because there are noise fluctuations. Now, of course, I could zoom here. I could look. This is a bird's eye look of my force extension distance curve. But I could go inside into the details, and then we start seeing more things. So we studied this problem, now that you asked, and we published a paper, which is this paper you see here in the bottom, PRL 2009, where we address not this question of sequencing, as you are asking, which is very interesting, but this process or unzipping. The question is, how many base pairs open at a time? So do they open one after another, or they open in bunches, in avalanches of many base pairs? Because you see, when you do the experiment by, for example, pulling the DNA hairpin, you see, when you see these ribs are 20 base pairs that are open. You don't see the 20 letters here. So the same question you should ask here, could I sequence this? And we know that sequence here, we have a single jump, because as you remember by the works of Michael Woodside, this takes microseconds. So if I want to see what is in here, I need to see, so these letters are in the transition state. So what we discovered is that we have bunches, avalanches, that in this unzipping experiment open sometimes 5 base pairs at a time, sometimes 100 base pairs. Is a power law distribution. It's like the fracture problem in physics that has been studied in other contexts. But then the letters reside in transition state. So good luck, but it would be beautiful to do it. So I have ideas on this. If you're interested. Okay.
That's very interesting. Thanks very much. Okay, so I think this is probably the last question. If people have other questions, of course, go ahead and write them in the chat. But Gabriel Langi has a question. So Gabriel says, thank you for the talk. Slightly off-topic question. Is there any perspective to combine the mechanical motion with other degrees of freedom, such as using a magnetic particle, for instance?
Magnetic particle has been used in magnetic tweezers. And combining, as far as I know, combining optical tweezers with magnetic tweezers has not been extremely successful. But I am not so much aware about the latest developments in instrumentation. I know that some of the particles that have been used for optical tweezers, because they have some sort of because you don't want them to be plastic, right? I mean, you want them to have some sort of super paramagnetic properties to respond in a field. If you use plastic or silica, you won't get any magnetization out of them. So you need to use particles that have some degree of magnetization. But as you know, in physics, magnetism comes from metals. So you have to put some sort of metal compounds in your particles. So you have to use some sort of complex alloys. But when you put a bit of metal, when there is the light of the optical trap going there, because these beads are illuminated, then there start being hard resonances, and sometimes even the beads explode. So it's not easy to get light with magnetics to operate at the same time. But as I said in the beginning, there could be latest developments of which I'm not aware of.
Okay, thanks very much. Yeah, so we do have some more questions. So Onur Pusuluk asks, is it possible to investigate the nuclear quantum effects in interbase hydrogen bonds using tweezers?
Which effects?
Nuclear quantum effects is the question.
Wow.
If you don't know what that means, I'm afraid I don't know what that means.
Well, I think, that's a good question also, because everything what we see, of course, is at room temperature, okay? So if you insist, we can go to 4 Celsius, 3 Celsius. Below 0 Celsius, water freezes. So we are not allowed to do biology or to do a molecule, a DNA, at least these sort of unzipping experiments. We cannot do them below 0, of course. Mm-hmm. Now, if you ask what is quantum and what is not in my experiments, I think that at the end of the day, what we see as classical is related to quantum, and this is something that could be debated, okay, could be disputed. But you see, most of these interactions that hold the 2 strands together are what we call pi stacking interactions between the bases. The bases are planar molecules which have a very small dipole. They are apolar. That's the reason why, by the way, there is this double helix. Double helix comes from the fact that bases are hydrophobic. They are apolar. They don't have dipole moments. They don't have permanent dipole moments. Okay, they have a small fluctuating dipole, and this gives rise to this effect, which is the van der Waals attraction. Okay, it's called van der Waals. Other people call hydrophobic. Other people call London dispersion forces. It's the fluctuating dipoles between the nearest neighboring bases along each strand make the bases pile up on top of each other. Now, this effect, to me, is like the Casimir effect. It's a quantum effect. Now, the fluctuating dipole effect is quantum. So I don't know if the nuclei, I mean, nuclei I cannot tell you. probably we cannot see that. You should go to much higher energies. But that indirectly there is some sort of quantum effects going there, well, that's a big question. I don't know. I would like to say yes, but I don't dare to say it. But I would like.
Okay, thanks very much. Interesting. So we have another question from Devira Segal, who asks about the avalanche unzipping that you were just talking about. So she says you could still engineer sequences, say, of only G's or A's and see differences. Is it interesting?
Yeah, indeed, this has been done. You can engineer sequences with different dinucleotide. Dinucleotide means two base pairs consecutive to each other. Dinucleotides, or trinucleotides, or tetranucleotides, different letters, and see how much they change the stability of the double helix in that position. This has been done. You can also study defects. So you can put, instead of putting a base pair GC, you can put CC or something that doesn't form base pairs according to Watson-Crick. So it doesn't match the geometry of the double helix. So this has been done and is useful. And I think it's something that is coming out more and more. And it will be more important as chemists start using optical tweezers as a common tool in the lab.
Okay, thanks very much. Yeah, so we've had quite a few questions. I don't think there's any more, so I think that's probably a good place to conclude. I'm sure if anyone in the audience has any further questions about anything, you can just email Felix and ask there. Yeah, so thanks very much to everyone for tuning in, and a big thank you to Professor Felix Ritort for a super interesting talk. Thank you very much for joining us.
Thank you very much, guys. Thank you for listening to me, and have a great day.